we are not going anywhere beyond the moon. You can often hear this claim, and it is usually justified by the notorious cosmic radiation, which could, And what's beyond the moon anyway? Some people even claim that human never went to the moon itself, citing Earth's radiation belts, which supposedly form an insurmountable barrier. But I think many of you already know that space radiation, even though it comes in different forms, is indeed dangerous and poses a serious threat even for relatively short missions to Mars or long-term stays on the moon. And if one day we want to send humans, say, to Jupiter, build colonies on Callisto, or even embark on interstellar journeys, we'll have to do something about it. And radiation can be dangerous not only for living organisms, but also for spacecraft and equipment. The topic of cosmic radiation as one of the main problems for spaceflight is discussed quite often. Someone could say, yes, there is a danger, but the issue can be solved with a sufficient level of protection. We can build that protection, but it would add a lot of extra mass, so what should we do? And when we talk about future space missions, we estimate what kind of radiation and in what amounts astronauts or robots will be exposed to. And then we start thinking about how to protect ourselves from this and how to come up with a method that won't make the spacecraft weight several times more. A method that won't launch the mission's budget into space instead of people. But of course it's not that simple, and even a super thick layer of shielding might not be a cure-all. As for spacecraft, on one hand, we've been sending them for decades to places with very different conditions, from near-Earth space to the Sun's outer atmosphere and all the way to the outer edges of the solar system. This allows us to gather some data on how radiation has affected these spacecraft and whether it has caused any damage. But humans haven't gone beyond the moon yet. Our knowledge of the actual effects of cosmic radiation on people is still very limited. Maybe it's not as scary as we think? So let's take a look at the fate of real spacecraft that have already flown and how space affected them. Let's talk a bit about radiation itself, its types, and how to protect against it. About the different regions in the solar system and beyond, and where the threat is higher or lower. How we study the effects of space on humans, especially in the places where no person has ever been, and not only that. I'm Andrei, and this is Cosmos Elementary. When it comes to radiation, space radiation and radiation in general, there are quite a few misconceptions, and they even spill over into everyday life. Just think of the people who are afraid of microwaves or Wi-Fi. Often confusion arises partially because of the very word radiation. The word radiation is used to describe a variety of phenomena. It can refer to that very scary radiation and also to ordinary visible light. And we don't seem to be afraid of that. Anyway, space radiation is a very broad term. And radiation can be of different types, come from various sources, and it has varying levels of danger. Some types are easier to protect against, while others are more difficult. And space itself isn't exactly the same everywhere either. Conditions in near-Earth orbit, around Mercury, near Jupiter, or in interstellar space can differ greatly. And it's not just a matter of distance from the Sun. The measures we take to protect against radiation when sending a robotic mission or humans into space will naturally differ depending on exactly where we are sending them. So let's talk about both types and sources of radiation and how they vary depending on location. Now, would you really call this pole and the light by the same name? Yet the difference between some types of space radiation is roughly the same. It can be electromagnetic radiation, massless particles or waves, photons, or it can be various massive particles of matter, electrons, protons, even entire atomic nuclei. We should also remember that radiation can be ionizing and non-ionizing. In general, both can be dangerous to some degree, but ionizing radiation is considered far more hazardous. The key difference, of course, is in energy. Ionizing radiation consists of massive particles or photons with much higher energy. enough to actually ionize the atoms or molecules they interact with. It directly damages atoms and molecules by knocking electrons off them, turning the affected particles into ions. Ionizing radiation also comes in different types. Several types are usually distinguished. Among electromagnetic radiation, this includes photons with the highest energy, X-rays, and of course, gamma rays. Among non-electromagnetic radiation, these can be alpha particles, for example, helium nuclei moving at high speeds, and beta particles, electrons and positrons. There can also be other types of particles. The specific type of damage depends on the particle's properties. If we're not talking about photons, then its mass, speed, and charge determine how deeply it can penetrate and what kind of harm it can cause. And there are also secondary particles, which we'll talk about later. This type of radiation can cause serious damage to both humans and equipment. And this is the very scary radiation we all worry about, ionizing radiation. Non-ionizing radiation essentially includes the rest of the electromagnetic spectrum, excluding X-rays and gamma rays, radio waves, microwaves, infrared, visible light, and some ultraviolet. Non-ionizing radiation can also be hazardous in its own way, especially ultraviolet radiation. Like ionizing radiation, it can cause certain types of cancer in humans, although the mechanism is somewhat different. Ultraviolet photons don't knock electrons off atoms, but through photochemical reactions, they can trigger processes similar to the effects of ionization. For example, they can produce free radicals that damage cells, leading to skin cancer. And here's what amuses me. The same people who are afraid of Wi-Fi or cell phone signals stick useless stickers on their phones or even put them in Faraday cage at night. And yet it doesn't bother them that they are constantly exposed to radiation from a far more powerful source of electromagnetic waves and of even higher energy radiation. Of course, I'm talking about the sun. As I mentioned earlier, some people don't even bother using sunscreen. Meanwhile, in a sense, space radiation scared people long before the space age. For example, in the form of comets, which were often considered a bad omen. The formation of one of a comet's tails, the ion or gas tail, is linked to the impact of charged particles from the solar wind. Or take auroras. So, people observed the effects of cosmic radiation without even realizing their true nature. But over the past 100 or so years, we've learned quite a bit about the nature of cosmic radiation. So we have particles that can cause damage to both the body and equipment. And within the solar system, there are two main sources of these particles. First of all, it's of course the sun. It emits across the entire electromagnetic spectrum, including X-rays and gamma rays, and it is also a source of massive particles. Here, too, we can distinguish two types. First, the constant stream of particles known as the solar wind, which consists of protons, electrons, and alpha particles. The energy of these particles isn't very high. But there are also so-called solar particle events, short-term events in which particles are accelerated to much higher speeds. They possess much greater energy and are of course far more dangerous. Many have probably guessed that this refers to solar flares and coronal mass ejections. And secondly, high-energy particles come to us from beyond the solar system, the galactic cosmic rays. They consist of roughly 85% protons, 14% helium nuclei, and other high-energy particles, including heavy nuclei like iron. Galactic rays are far more dangerous, if only because the events that set them traveling through the galaxy are much more powerful than, for example, the processes responsible for the solar wind or even coronal mass ejections. In the case of galactic rays, supernovae are most likely to blame. As a result, these particles travel through the galaxy at speeds close to the speed of light. For comparison, the speed of solar wind particles is a few hundred kilometers or miles per second, while coronal mass ejections can reach several thousand kilometers or miles per second, still far from near light speed. It's quite likely, by the way, that some of these particles come to us from other galaxies. But those are the sources. And remember, I also mentioned that the radiation environment varies from place to place. For example, when we talk about circumplanetary space, the situation differs from planet to planet. And it's not just a matter of distance from the Sun. A significant factor is whether the planet has a strong enough magnetic field. For example, in near-Earth space, there is what's called periodic or temporary radiation. This comes from solar flares and ejections. There are also trapped particles, charged particles that get caught in Earth's magnetosphere and remain there. As a result, around the planet, regions form where a permanent amount of dangerous charged particles exist. These are those scary Van Allen belts. In low Earth orbit, the protection of the magnetic field still works well. So the situation up to Van Allen belts is one thing. Inside them, the situation is different. On the surface of the Moon, there is no protection from Earth's atmosphere or magnetosphere, so both solar and galactic particles can have a greater impact. Mars does have an atmosphere, but it's very thin, and there is no global magnetic field. A similar story is in interplanetary space. For example, while traveling to Mars, we are exposed to both solar and galactic particles. Interestingly, on the surface of Mars, the situation can actually be a bit better than in interplanetary space, partially because the planet itself acts as a natural shield against radiation. But in interplanetary space, galactic rays hit us from all directions. If we or a spacecraft are heading to Jupiter, we also need to account for trapped particles in its magnetosphere, in regions similar to Earth's Van Allen belts. Additionally, Io adds to this with its volcanic eruptions. The Sun's activity cycles also play an important role. Intuitively, one might think that the most dangerous periods are when the Sun is the most active. But even here, it's not that simple. On one hand, during solar minimum, there are far fewer flares. On the other hand, the flux of galactic particles is connected to solar activity. How? Just as Earth's magnetic field protects the planet from cosmic rays, the Sun's magnetic field shields the solar system from galactic rays. During periods of minimal activity, the Sun's magnetic field weakens, which means less protection from particles coming from beyond the solar system. And as a result, the flux of galactic rays is stronger at that time. And from this, it also becomes clear why space radiation is such a problem for potential interstellar travel. After all, we live the heliosphere, the bubble created by the Sun. And beyond it, the flux of galactic rays is much more dangerous. Sure, we don't have to worry about the solar wind and flares there, but their energy is much lower than that of galactic rays. Plus, if we assume that an interstellar spacecraft will travel at relativistic speeds, with a significant fraction of the speed of light, the rapidly moving spacecraft would collide with the already extremely energetic particle flux. In short, it doesn't sound very promising. From everything I've explained so far, it's already clear that the problem of cosmic radiation for spaceflight is complex and multifaceted. We need to consider where we're going or sending a robot, what conditions we'll encounter, the timing, and which type of radiation will be the most dangerous in each specific case. In general, this is clearly not a problem that can be solved simply by surrounding yourself with a thick layer of lead, especially since that wouldn't be a good idea either. The essence of damage caused by cosmic rays can be simplified as follows. A particle has high energy, it collides with and penetrates that material of the spacecraft or the tissue of the body and transfers that energy to that substance, which is bad. But the exact nature of the damage, how deeply a particle penetrates, depends on the type of radiation, the properties of the material, the environment, and other factors. And indeed, the effects can vary. So, how exactly do they occur? The most common process is ionization, which we have already discussed. This occurs when a cosmic radiation particle either knocks electrons off or adds electrons to the particles in a satellite or spacecraft material. But ionization can take different forms. It can occur through the interaction of the fields of charged cosmic radiation particles with particles in the spacecraft, and uncharged particles, like neutrons, can also cause ionization through direct collisions. If we're talking about electromagnetic radiation, for example, when an electron absorbs gamma photons, it gains enough energy to leave its atom. At sufficiently high gamma photon energies, they can also interact with atomic fields and additionally produce electron-positron pairs, which then can annihilate. As a result, additional gamma photons are produced, which are themselves ionizing. There is so-called Bremsstrahlung radiation, which occurs when a charged cosmic particle passes through matter and interacts with fields within it, causing the particle to emit additional photons, creating something like a shock wave. When cosmic radiation interacts with atomic nuclei in spacecraft materials, it can alter or break these nuclei, producing additional secondary radiation, which can also be hazardous. And that's not all. But again, we see that it's a bit more complicated than just a particle, boom, ouch. Now, how exactly can these and other effects impact spacecraft? Well, for example, a spacecraft can become electrically charged. Elon Musk didn't actually send his Tesla to space to charge a dead battery for free. This is a slightly different story. For example, the surface of a spacecraft, say in low Earth orbit, can accumulate charge. This can create a potential difference between the surface and the surrounding plasma. A potential difference can also develop between different parts of the spacecraft. Charge can accumulate not only on the surface but also inside, in instruments and components, if particles penetrate deeper, which can be even more dangerous. As a result, electrical discharges can occur. They can cause structural damage and affect the operation of equipment, microprocessors, sensors, and so on. The extent of the damage can vary from errors that can be fixed, well, roughly speaking, by a reboot, to permanent damage. Also distinguish a single event effect, when literally just one particle, say a high-energy proton arriving from beyond the solar system, hits a microchip and it can cause an error, and that's just a single event. Although they also talk about the total ionizing dose for a spacecraft. The amount of radiation can reach a level where a satellite or spacecraft completely fails, and no amount of rebooting will save it. Interestingly, the first satellite in history to fail this way didn't do so because of natural cosmic radiation, but we broke it ourselves. It was the Telstar satellite, launched in 1962. At that time, nuclear tests were being conducted in space, a project called Starfish Prime. A powerful 1.4 megaton device was detonated in low Earth orbit at an altitude of 400 kilometers, roughly the height of ISS orbit. As a result of the explosion, a huge number of beta particles were released. They became trapped in Earth's magnetic field, which led to the formation of an artificial radiation belt, and this electron belt persisted for several years. As a result, the Telstar satellite received a radiation dose 100 times higher than it was supposed to survive, and it failed. This nuclear test destroyed 7 satellites, most of which were rendered inoperable due to damage to their solar panels. Space particles can also cause what could be described as mechanical or structural damage to a spacecraft and its components. Defects form in atomic and molecular bonds. Well, in other words, tiny holes appear. The degree and nature of the damage depend on the location. And interestingly, it is far from uniform even near Earth. For example, there's a well-known South Atlantic magnetic anomaly, a kind of a dent in Earth's magnetic field. In this region, the inner Van Allen radiation belt comes as close as about 200 kilometers or 124 miles to Earth's surface. Satellites, of course, orbit higher than that, and when they pass through this area, they are exposed to much more intense radiation. For example, here is a map showing single event occurrences recorded by the SWARM mission. And as we can see, there is a high concentration of events in the region of South Atlantic magnetic anomaly. Overall, for satellites in near-Earth space, we have a fairly good understanding of how cosmic radiation affects them. After all, we have launched thousands of them. When a spacecraft ventures into interplanetary space, the data situation gets even worse. When a spacecraft is far away and problems arise, we cannot always confidently identify the cause, because we are much less familiar with the environment the spacecraft is operating in. But there have still been failures that can, with a high degree of confidence, be attributed to space radiation. As an example, we can look at the Galileo spacecraft, which studied the Jupiter system. The spacecraft was equipped with a star scanner or tracker used to control its orientation. By observing bright stars, the spacecraft could determine its orientation in space. However, charged particles with sufficient energy were detected by the scanner as light. It was designed to orient itself based on objects of a certain brightness, but objects below that brightness level, as well as signals from cosmic rays, were interpreted as noise. However, there were cases when the instrument mistook signals from cosmic rays for a star. This confused it. The spacecraft, kind of thought it was pointing in the wrong direction, and a correction command was issued. The scanner data didn't match the gyroscope data, and ultimately the fault tracking system triggered, switching the spacecraft into a different operational mode. There were instances when this happened twice within 8 hours, and if it had occurred 2 more times, the spacecraft would have gone into safe mode. There were also other malfunctions related to this instrument. Radiation also caused malfunctions in another orientation system, the gyroscope system. As a result, the spacecraft, quote-unquote, believed its antenna was pointing not at Earth. The thrusters fired, and the spacecraft ended up oriented in an unknown direction. Fortunately, another antenna was still transmitting a signal to Earth, and the situation was manually corrected. In the early stages of the mission, the system connecting the rotating and non-rotating parts of the spacecraft also experienced sudden resets, which were also attributed to cosmic radiation. There were malfunctions in memory chips, cameras, the spectrometer, the particle detector, and the excess noise appeared in the data from several instruments, as well as other key scientific and navigation devices. The list is quite extensive, and it is all detailed in this paper, where malfunctions are categorized not only by instrument but also by the level of confidence that cosmic rays were indeed the cause. Overall, radiation caused the Galileo mission team quite a few headaches, yet the spacecraft still managed to operate longer than originally planned and successfully completed its mission. Nevertheless, even the example of this single spacecraft demonstrates quite well how little we know about more distant regions, such as the Jupiter system and interplanetary space. And the farther from Earth, the less we know. Although the Voyagers, in one way or another, are still operational over 48 years after their launch, and continue to transmit unique and valuable information about conditions beyond the heliosphere. Although they are much simpler spacecraft. On one hand, we have been launching spacecraft for several decades now. They operate and accomplish their missions. On the other hand, mission objectives are set partially with these potential problems in mind. If we could avoid them, spacecraft would be able to operate longer and accomplish even more. The farther we send a spacecraft and the more complex the mission, the greater the risks. Simply hoping that luck will protect it, that radiation won't cause serious problems or even disable the spacecraft entirely, doesn't seem like the best strategy. So we need to develop new ways of protection, and when it comes to sending humans into space, the stakes become even higher. On the surface of the Earth, we're lucky. We can thank our dense atmosphere and strong magnetic field. Speaking of the atmosphere, most of the dangerous electromagnetic radiation doesn't reach us, except for some ultraviolet radiation. But even when we climb a high mountain or fly in an airplane, we are exposed to stronger radiation. But there is no need to rush to cancel your vacation plans. On average, one airplane flight exposes your body to about the same radiation as a single X-ray. Still, most of us don't spend extended periods at that altitude. Pilots' work, and even more so astronauts, is considered a job with increased radiation exposure. At an altitude of 12 kilometers, radiation levels are 20 to 40 times higher than at sea level. On routes that pass over the poles, radiation is 3 times higher than on equatorial routes. During periods of intense solar activity, levels can rise by another factor of 3. And as soon as we go into space, the situation becomes even worse. So far, most people who have been to space have stayed in low Earth orbit, plus the astronauts of the Apollo missions who went to the moon. Years of experience show that in low Earth orbit, outside the radiation belts, humans can stay for a certain period without serious or obvious harm to their health. There, although people lose the protection of the atmosphere, they still have the protection of the magnetic field. Naturally, this doesn't mean there is no danger, and measures are taken to reduce the risks. Overall, nowadays, no one doubts that humans can relatively safely stay there, provided certain limits and precautions. But what some people doubt is whether we can actually travel farther, and some of the information can indeed be alarming. For example, this article in the journal Nature tells us this: beyond low Earth orbit, every cell nucleus in a human body will be hit by a proton or a secondary particle once every few days. Every single one. And once every few months by a heavier ion, like silicon or iron ions. I don't know about you, but I wouldn't be very comfortable knowing that a potentially dangerous particle passes through every cell in my body. Of the particles I just mentioned, the heavier ions, despite being rarer, are responsible for most of the accumulated radiation dose. These particles can generate free radicals in the body, causing damage to cells, and long-term exposure can lead to premature aging, cardiovascular diseases, the cataracts. It can also harm body tissues and the nervous system. Moreover, the threat comes not only from the direct impact of these particles. When they interact with the spacecraft structure and shielding, they produce secondary particle streams, which can be even more dangerous to the body than the primary particles. Particles arriving after coronal mass ejections have lower energy and cause less damage to the skin and internal organs, but they can still be dangerous, especially during spacewalks and on longer-term missions. Another problem is that the flux of such particles is not constant, and it is difficult to predict. While especially powerful and dangerous events are rare, they do occur from time to time. For example, the major storm in 1989. And the effects of such short but intense events can range from weakness and nausea to, well, in extreme cases, death. Different forms of cosmic radiation can also damage DNA in cells and are believed to potentially cause cancer. One of the main problems is that beyond low Earth orbit, only the astronauts of the Apollo missions have so far traveled. And there, although they were exposed to different conditions, it was only for a short time. The Apollo missions lasted just a few days, and we don't really know how the human body would respond, for example, during a several-month-long flight to Mars. So far, research on the possible effects of long-duration spaceflight on humans is limited to using models and experiments with analogs. For example, in the lab, a particle beam is created and researchers observe the effects it has on animals. But the problem is that these analogs are far from replicating the complex radiation environment of deep space. In general, the results of such studies contain a lot of uncertainties, especially when it comes to the long-term effects of cosmic radiation. So we may not know for sure what the effects will be until humans actually establish a permanent presence on the moon and travel to Mars. But ideally, we'd like to get there without getting fried. So we have to come up with some form of protection, even with limited data. In general, approaches to protecting against cosmic radiation can vary. And again, they depend on where we are going, for how long, and so on. Again, one might think that it all comes down to slapping on a thicker shield. But, as I've already said, it's not that simple. Protection can be passive or active, and it can also involve certain procedures and careful mission planning. In addition, protective measures can be targeted at specific effects. For example, among the problems that occur with spacecraft, I mentioned the accumulation of charge on the surface of the spacecraft or on its individual components. Here, the goal can be not to prevent particles from creating a charge, but to remove it. For this, systems can be used that either emit electrons or conversely capture ions to neutralize the charge. Errors caused in a spacecraft's electronics by individual particles can be mitigated using specialized software. But large-scale damage, structural damage, and especially harm to human health is better prevented from the start. In some cases, simply planning the mission properly can significantly reduce the risk. A good example here is the Apollo missions, which I've mentioned several times today. At the very beginning, I mentioned that some people use Van Allen belts as an argument trying to prove that humans never went to the moon. We've already established that these are regions of increased radiation where charged particles get trapped for long periods. For some reason, those who use this argument to prove that we never went to the moon don't bother to simply read about how the Apollo missions actually flew through them. The thing is, yes, the belts are indeed dangerous, and I wouldn't recommend lingering there for long if you ever fly beyond low Earth orbit. But the Apollo astronauts didn't linger there either. Not only that, they passed through them quickly, and the astronauts spent a total of about 6 hours there, considering the entire round trip. The belts are also non-uniform, and the flight trajectory was specifically chosen to avoid the most dangerous regions, which are located near the equator. So in the case of a flight to the moon, it is entirely possible to plan it in a way that minimizes exposure in the belts. What is difficult to plan for is solar activity. Of course, it was actively monitored, but the risks were still present. During the Apollo era, the situation and approach to safety were entirely different. Back then, they partially relied on luck as well. Nowadays, forecasting and monitoring of space weather are much better than they were in the 1970s. In a large NASA document dedicated to the problem of space radiation, it is stated that for now, while humans are only staying in low Earth orbit, the main method of protecting people from radiation in space is simply limiting the time spent in space, usually to 3 to 6 months per mission, limiting the duration of spacewalks, and again planning missions with solar activity periods in mind. Of course, this doesn't mean that there is no protection at all. On the ISS, hydrogen-rich shielding is used. Special layers of polyethylene protect the areas where astronauts spend the most time. Polyethylene might sound a bit funny, like they just wrap themselves in plastic bags, But it is important to remember that radiation comes in different types, with varying levels of penetration. Alpha particles can be stopped even by a sheet of paper, beta particles by a sheet of aluminum, but gamma rays and high-energy galactic cosmic rays can penetrate very deeply. Even a fairly thick layer of shielding may not provide full protection. Still, the ISS is far from being in the worst conditions. Therefore, their modest shielding and time limits are sufficient, which, of course, does not provide complete protection from radiation. But if you travel farther, these measures won't be enough, and some things might be downright impossible. A one-way trip to Mars takes at least several months, and a round trip with short stay on the planet would take about 2 years, all in much harsher radiation conditions. In general, in this case, there is no way around having shielding that prevents dangerous particles from reaching us and the equipment. That's why questions arise when looking at images of lunar and Martian bases. Ideally, living modules should be covered with thick metal shielding or a layer of water which provides good radiation protection, or both. Water is needed anyway for the crew, so the extra mass isn't as critical. But hauling a lot of extra metal would, of course, be very expensive. Part of this can be compensated by using local materials. One suggestion is to cover the habitat with a thick layer of regolith, or even to build bases inside underground caves and lava tubes. But aboard the spacecraft, there is no regolith or caves. We need shields. Here we can recall the two main approaches: passive and active protection. Passive protection is simply placing a barrier between the inside of the spacecraft and the external radiation. The advantage of this approach is that if the shield is thick enough and made of right material, it doesn't matter which particles are coming, charged or uncharged. On Earth, people also encounter ionizing radiation, for example, when working with radioactive materials, and in such cases, passive shielding is usually used. Surely you've worn a special apron at least once when getting an X-ray, or seen special containers used for storage. Theoretically, yes, a spacecraft could be surrounded by a thick layer of shielding. But here we again run into a problem with the cost of the mission, since every kilogram counts. Suppose we place a 7 cm thick metal shield. That would add a lot of mass to the spacecraft and could make the mission so expensive that it becomes impractical. But the funniest part is that such a shield still wouldn't block all radiation, only about 30%. And as I already mentioned, with passive shielding, there's also the problem of secondary particle production. The primary particle may be stopped, but the secondary particles can penetrate inside and be even more dangerous. This means that the shield would need to be even thicker. Here's an interesting point. Many people associate radiation shielding with lead, but such a shield can actually produce even more secondary particles. Lighter shields, made of carbon or hydrogen, are better in this regard. Again, water, which is necessary anyway, can be used as a shield, but water is heavier than polyethylene. As with traditional materials, it is still possible to achieve some protection on a long-duration flight. This can be both very expensive and not fully effective. That's why new materials need to be developed, and NASA is working on this. One example of a promising material is boron nitride nanotubes with added hydrogen. This material can be lightweight, effectively absorb high-energy particles, including secondary particles, while also being strong, able to withstand high temperatures and be flexible. It's even possible to make spacesuits from it, but for now, protection using this material is still in the development stage, and it's hard to say when it will be used in space. The idea of active protection sounds interesting. Here the concept is to take a page from the nature's book, or precisely near the Earth, which protects us with its magnetic field. And beyond it, we would need to create our own field. Magnetic or electric or a combination of fields can also be used, and plasma as well. The point is that these fields would simply deflect charged particles. This approach is currently being studied, and in the future it may well be used on spacecraft. Of course, there are certain limitations. For example, some of these shields will not deflect neutral particles, and an effective system also requires a power source, and so on. It is also possible to use a combination of passive and active protection. NASA is also looking at it from a completely different angle. The use of a special diet and medications to reduce the effects of radiation on the body. This could probably work to some extent in combination with other methods, but it certainly won't be a cure-all either. Existing technologies are still not sufficient to just put a person into a spacecraft right now and send them to Mars without worrying about their health. And at the same time, it couldn't be done without spending the equivalent of a medium-sized country's budget. New materials and protection technologies are needed. It is absolutely necessary to have more data about the conditions and their effects on humans beyond near-Earth space. Funny that in 2016, Elon Musk was already planning to send people to Mars in 2022. But, Still, for the solar system, at least in the future and perhaps not even in a very distant one, this is not an insurmountable problem. But for interstellar flight, everything becomes many times more complicated. If we travel slowly, even then we know even less about the conditions beyond the solar system, and here again, new methods are needed. And if we talk about speeds measured in percentages of the speed of light, there are high-energy particles, and even tiny dust particles drifting around at such velocities would cause significant damage. I already discussed this in more detail in my video about interstellar flights. To begin with, we should at least send some probes farther than the Voyagers and collect at least some data about what is happening in actual interstellar space. Although radiation, of course, is far from the only problem of interstellar flights, The real question is whether we will ever be able to do this at all. In any case, we can see that the problem is severe, multifaceted, it has many non-obvious aspects, we still don't know many things. But that doesn't mean that we won't be able to solve it all. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment, and subscribe for more videos in future, and share them with your friends. Thank you, and bye.